In this section, we'll look at radical expressions. We'll look at adding and subtracting them. And then towards the end, or maybe in a separate video, we'll take a look at rationalizing denominators. So we've simplified radicals, we've divided them. Now we're going to add, subtract, and multiply them, and then rationalize the denominator towards the end. So a lot of this comes down to simplifying first and then combining like terms. My reminder again, in the beginning, you can only add and subtract like terms, and sometimes the ones that don't look like are actually like terms once you simplify them. And that's why we spent all that time simplifying radicals, because that becomes an important step in the process here. So I'm not going to do every one of these, but let's take a look at the first one, right? 3 square root of 5 plus 9 square root of 5. Think of it this way. You've got 3 of something and 9 of the same thing. What do you have? You have 12 of them. In this case, 12 what? 12 square root of 5. So if you had a bucket full of square root of 5s and you put 3 of them in, and then you put 9 more of them in, you'd have 12 of them, but the item doesn't change. The items remain square root of 5s. So you have 12 what? 12 square root of 5s. Look at number 2. I've got square root of 3s and I got square root of 2s. So I can't combine these all into one expression. There's only a square root of 2 there, so I've got 4 square root of 2. But now look at my square root of 3s. I've got 8 of them. I take away 5 of them. I'm left with 3 of them. So I get a 4 square root of 2 and a 3 square root of 3. And that's the best that I can do with that. All right, look at number 4. Number 4 looks like completely unlike terms. I got a square root of 27, I got a square root of 243, and I got a square root of 12. Let's come over here and try simplifying them. The square root of 27, I can make, in terms of perfect squares, a square root of 9 and a square root of 3. So that becomes 3 square root of 3. So the square root of 27 is the same as 3 square root of 3. How about the square root of 243? Well, I can start working through my list of perfect squares. If I'm not sure, I don't know, try taking 9. I know 4 is not going to work. So let's try taking 9. Take 243 and divide it by 9, and I get 27. But that can be broken down further. So maybe I'll try something bigger than 9. How about 81? 243 divided by 81 is 3. Okay, so I can break the square root of 243 into the square root of 81 times the square root of 3. If you had done it with a 9, you would have gotten 9 and 27, but then you'd have to do it again. So if I can go for the biggest perfect square, I will. All right, so the square root of 81 is 9. So 243 breaks down into 9 square root of 3. How about 12? That seems like a relatively simple one. 12 breaks down into 4 and 3. Square root of 4 is 2. So I get 2 square root of 3. So when I come over here, I'm going to replace that square root of 27 with this 3 square root of 3. But don't forget there was already a 5 there to begin with, so don't lose that. There was already a 4. I'm going to replace that square root of 243 with a 9 square root of 3. Then a minus 2, and I'm going to replace that square root of 12 with a 2 square root of 3. So that gives me a 15 square root of 3 plus a 36 square root of 3 minus a 4 square root of 3. And oh look, now they're all the same term. Now they're all square root of 3s. So maybe I want to do 15 minus 4 is 11. And then 11 plus 36 is 47, so I get 47 square root of 3. Right, so it will take you some time maybe to go through and to simplify those radicals. Once you simplify the radicals, then you may find that all of them, like in this case, they were all square root of 3s, or you might find that they're a mix of, let's say, square root of 3s and square root of 2s, but you should be able to combine some of them. Unless somebody gives you a problem where you do all the simplifying and find out nothing combines. Well, at least now we know. All right, let's take a look at a couple of these up here. Let's take a look at number 5. Number 5 is a square root expression that involves not only constants, but variables as well. So the square root of 3x squared. Let's do the same thing we did before. Let's come up here and sort of simplify on the side. So the square root of 3x squared, I can think of as the square root of x squared times the square root of 3, which is x root 3. Okay, so this thing here simplifies to x root 3. How about the square root of 12x squared? Well, let's do our old perfect, not perfect thing for this. The x squared is perfect, so he goes over there. For the 12, I can break that down into 4 times 3. The 4 is the perfect square, the 3 is not. Don't lose constants along the way. That 3 comes down in front here. The square root of x squared is x. The square root of 4 is 2. So I get 2x times the square root of 3, which means that this expression here gets replaced by 2x square root of 3. Oh, look, this is the same expression. So I could have actually combined them first. But there's my 4 times 2x square root of 3. So I have an x square root of 3. I have a 6x square root of 3. And I have an 8x square root of 3. Let me do this. Now can you see what my terms are? I have 1 of them here, I have 6 of them there, and 8 of them there. 1 plus 6 is 7, plus 8 is 15, so I have 15 x square root of 3's. So maybe putting the parentheses around those x square root of 3's helps to identify what is the common term amongst all 3 of them. This way, when I go to add them, I'm making sure that I'm adding the whole term. So I had a 1x square root of 3, 6 more of them, 8 more of them. All right, look at number 7. Number 7 involves cube roots. So here, there's not a lot of simplifying that I can do because you notice those x's on the inside won't come out. But the cube root of 8 will. So the cube root of 8 is 2, and I'm left with a cube root of x. Over here, the cube root of 27 is 3, and I'm left with a cube root of x. So I have 2 cube root of x minus 18 cube root of x. So the cube root of x and the cube root of x, they are like terms. 2 of them subtracts 18 of them, gives me negative 16 of them. Negative 16 what? Negative 16 cube root of x. All right, so our goal is to try to simplify until we get a term that becomes a common term. Look at number 9. Number 9, I can actually turn that first term into a cube root of 7y over a cube root of 64, but a cube root of 64 is just 4, minus the cube root of 7y over 4. Turns out this answer is just 0. I'm subtracting something from itself, and I get 0. All right, what's the issue in number 10? They're both square root of 2's, right? So I have a 7 over 5, and I have a 3 over 3. All right. 2 ways to do this. One is common denominators right away. The other is to say I have 7/5 square root of 2 minus 1 square root of 2, right? 3 over 3 is just 1. So I'm subtracting 1 square root of 2. Why not make it 5/5 square root of 2? Now I've got 7/5 minus 5/5 gives me 2/5. 2/5 what? 2/5 square root of 2. All right, so I'm going to look at that 3/3 square root of 2 and just say, well, that's 1. If I can call it 3/3, why can't I call it 5/5? The other option, if you really want to, is to go down to 15ths. You can turn them all into 15ths, do the subtraction that way, and then simplify at the end. Oh, this says, how about this one? There must be something fun coming here. I've got a cube root of 343, a to the 7th, b to the 4th. What number times itself 3 times will give me 343? Let's see if it's a whole number. It's 7, right? Which you can do by hitting that cube root key on your calculator. Cube root of 343 comes out to be exactly 7. So the cube root, if I do a perfect cube, not perfect cube, all 343 goes over here. The a to the 7th, I'm pulling them out in groups of 3. So 6 of them go here, 1 of them go there, and I'm pulling out the b's in groups of 3. So 3 of them over here, 1 of them over there. We said the cube root of 343 was 7. Exponent, 6 divided by 3 is 2. 3 divided by 3 is 1. So this becomes 7a squared b, cube root of ab. Now look at that 27ab. 24 stays. Cube root of 27 is 3, right? Because 3 times 3 times 3 gives me 27. What's left under the radical? NAB. All right, so I'm going to pull out that cube root of AB. When I do that, what's left over here is a result of dividing each of those terms by the cube root of AB. So here I have a 7a squared b minus 24 times 3 is 72. And that's my answer. I can't combine those a squared b's and those 72's together because they're not like terms. If they were, then I could do something with them. So the best I can do is factor out that AB. All right, let's do multiplying and rationalizing denominators as a separate video.